We all got to know that the everyday matter is made out of small entities named atoms, and that these atoms are compounds of even smaller particles. A bunch of electrons, called the electron cloud, orbit in a grouping of protons and neutrons called the nucleus. We also got to know that there are particles, other than the ones I previously mentioned, such as photons making up light. In addition to this, the lucky minority were told that even protons and neutrons are made out of quarks, tiny particles having no internal structure, which means they are indivisible, just like photons and electrons, and that there are many similar particles called fundamental. They are either fermions, the particles making up matter, gathering quarks or leptons, or bosons, the particles responsible for transmitting energy, gathering gauge bosons and a single scalar boson. But if these so-called fundamental particles are uncuttable, what are they made out of? Well, no one can answer that one for sure. But the string theory gives the most logical and practical answer, claims that all fundamental particles are one-dimensional vibrating strings of energy, and that the vibrational pattern of the string is what determines the properties of the particle, mass, charge, and spin, and defines the particle in question. Wait, that's not it. The string theory has other principles. Supersymmetry, which is another basic element of the string theory, states that for every fermion, there is a corresponding boson, related in that way matter and forces. Unfortunately, the particles needed to prove this one right have not yet been detected by experiments. And since it is a unified theory, it attempts to unify the four known forces: electromagnetic force, strong or weak nuclear force, and gravity, by assuming they all are strings interacting with each other. And in so doing, it unifies general relativity and quantum mechanics, two different fields of study that didn't agree that much before, because general relativity, with its strong gravitational fields, implies a smooth-flowing universe, while quantum mechanics, with its uncertainty, implies a turbulent and chaotic universe on a micro scale. But the conflict has ended, luckily. Well, theoretically at least. Everything seems good so far. Oh wait, the theory cannot be consistent on three-dimensional work. There has to be more dimensions out there to work this out. Well, don't panic, it's just another part of our famous theory. It predicts that our universe has a total of 10 dimensions, 3 of which are the spatial ones we are all familiar with: back, front, up, down, left, and right. They're extended, that's why we can see them. The fourth one is time, as we all know it. The 6 other dimensions are spatial as well, but can't be observed because they are curled up to incredibly small sizes. They can be represented in the Calabi-Yau manifold. See, this theory is undoubtedly a promising one, but as theoretical physics remains an uncertain science, the truth remains uncovered.